Welcome, colleagues, to our final keynote session for the conference. And I can see all of you, you managed to get here. We apologize for the slight delay because they had to reconfigure this room. As you would recall, by 5 o'clock when we left here, this room was not like this. So a lot of work had to get into this. So we appreciate the work that went in because it transformed for the better. So for the keynote session, we will have Professor Thomas Sterling, who will deliver the keynote address. I think to most of us here in the high-performance computing community, Professor Sterling is well known, but I will nevertheless go through his bio that is also there in the program. So Professor Sterling is a senior research scientist and a director of the Department of Advanced Future Computing at the Texas Advanced Computing Center at the University of Texas at Austin. For the past 13 years, he was a full professor at Indiana University in Bloomington School of Informatics, Computing and Engineering. Since receiving his PhD from MIT as a Hertz Fellow in 1984, Dr. Sterling has engaged in applied research in parallel computing system structures, semantics, and operation in industry, government, labs, and academia. Professional affiliations have included the Harris Corporation, IDA Supercomputing Research Center, NASA of Maryland, Caltech, Louisiana State University. Dr. Sterling is best known as the father of the Beowulf. If you don't know what that Beowulf is, Professor Sterling pioneered us to be able to have access to clustering of commodity clusters. Thomas wants to make sure that we emphasize commodity clusters. So basically, to lower the barrier for us to be able to get to supercomputers. And that was the start of the high-performance computing. Professor Sterling, for that, he got the Gordon Bell Prize in 1997. His current research is associated with innovative extreme-scale computing through memory-centric, non-von Neumann architecture concepts to accelerate the dynamic graph processing for AI, including machine learning. Professor Sterling was the recipient of the 2013 Vanguard Award. He's a fellow of the AAS and has been inducted in the Space Technology Hall of Fame. Professor Sterling is co-author of 7 books and holds 6 patents. Most recently, he co-authored the introductory textbook in high-performance computing. And I can attest that this textbook, the first time it was introduced, he brought it here in South Africa. And we started using it in our high-performance computing. So that shows you that Professor Sterling is a friend of South Africa because when he authored this book, he brought it here so that we can start the high-performance computing curriculum in our universities, but also that we have been using in CHPC. I think what is not included here is that Professor Sterling, at the supercomputing that was held in Atlanta, he was also recognized as one of the legends, 35 legends that pioneered the development of high-performance computing over the past 35 years. So with this, colleagues, I would like you to help me welcome Professor Thomas Sterling to stage so that he can share with us the past and whatever happened in high-performance computing, but also true to his talk, and that's why we put it at the end, provocative and what we should expect in future on high-performance computing. Welcome, Tom.
Thank you very much. Well, it is a true delight for me to be welcomed by you in this a very beautiful setting. And as I unfortunately missed last year's conference, I consider this a returning to home. This is where I feel I belong and I live, and it has been a wonderful experience to work with Happy, Werner, and many colleagues over uncounted years. I wish to talk really about two but closely related things. There have been occasions when I have presented implications for recent events and so forth. Not this time, because we are at a very special time in the field of high-performance computing, and you all see it. The close relationship now with artificial intelligence, I should say artificial intelligence 2, because this is a field that has existed since 1959, and machine learning, a more recent but not that recent event, and many more specializations such as large language models, which we are even today just learning to understand. Well, there we go. Thank you. So let me start with the bad news. And this is not a good way to start a talk, is it? I'm supposed to be telling you all the good news, and I'm starting with the problem. But we are at a turning point, without exaggeration. And this is because the field and the technologies which have existed for 70 years, is flatlining, is coming to an end. Part of this is due to the change in the technology feature size, which for the first time is now in the single-digit nanoscale. Just to place nanoscale, 1 nanometer is only 10 atomic distances apart. And that's for the smaller atoms. So we are in the teens of feature size. We can't get smaller than an atom. We can't get as small as an atom. The second problem is clock rates. The time it takes for the smallest incremental change in a computer system. Now, I hate to admit this, but I'm older than almost everybody here. I really hate to admit that, by the way. But I made it up to the stage all by myself. So, when I was born, so was the first digital electronic computer. There were two in the UK. One was the Mark I, the Manchester Mark I, and a few months later, and probably for all considerations, the real prototype was the machine out of Cambridge. Morris Wilks was the principal investigator. He was young. This is 1940. I know, I have to admit it. It was 1949. And for those following 70 years, the von Neumann model was first codified, excuse me, was first codified in 1945. Von Neumann was taking the train trip from Pennsylvania to Los Alamos National Lab. That wasn't 5 hours, that was more like 3.5 days. And he wrote this paper. But he only finished it that he was completing it. The train was pulling in to Los Alamos. Actually, it wasn't Los Alamos, to be honest. It was Santa Fe. Then there was a drive up a hill. I've taken that drive. So he only had time to put one name on the paper, and he put his own. And so that paper, which I suggest that all of you read at some point in your career, only has the one name, because he worked with Eckert and Mauchly at the University of Pennsylvania. I hope I have that right. Throughout the war, and was, among other things, instrumental in the creation of the machine that would become the first von Neumann machine in the field. Now, von Neumann, I have to mention this side story. Von Neumann also created the first non-von Neumann computer. Well, he, in 1949 or 1950, he developed conceptually the cellular automata machine. And this is the class of machine that, to this day, has close ties, at least in special purpose computing. Von Neumann entered his career working at the Institute for Advanced Studies in Princeton University. In addition to clock rates largely flatlining, coming to the end of a growth that grew exponentially over, well, almost 70 years, the size of these machines, at least starting in and around 1990, also grew dramatically. It's complicated. I was going to say exponentially. I don't believe it is. It's probably polynomial. But today, we have the largest machines that were at 10,000 square feet foot pad, which is, on the order of 1,000 square meters. I know we talk in not just imperial units. More recently, in fact, I can be specific, in 2000, no, that's not right. Well, sometime in the last 30 years, machines also became heterogeneous, including the adding of GPUs. GPU stands for General Processing Unit or Graphic Processing Unit. And now, to this day, they have become, if not a dominant, at least a very large part of computing. The GPUs have given a kind of boost to performance, and as a result, have forced us to create heterogeneous computers. Now, that would be a good thing, although it's really part of the bad news, because now you're computing two different kinds of machines. You're using two different kinds of machines instead of just one. And while people say, well, you can use both at the same time, yes, you can. You can use both, but the truth is that's too hard. Really too hard to uniformly use both kinds of machines for. So routinely, heterogeneous computing using GPUs switches back and forth from CPUs, central processing units, to setting up and running GPUs, which for certain kinds of problems will go much faster, but only for certain kinds, and then back to the CPUs. 2 years ago, the first machine at the level of, well, we call it exascale computing. This is the exaflops machine. For those of us who have lived through the entire lifetime of digital computers, that's quite a trip. The digital computers had throughput, and I'm thinking now about Morris Wilks' EDSAC machine, of less than 1,000 flops, less than 1,000 floating point operations per second. Within the last 2 to 3 years, we have now delivered the first 3 exascale machines, or exaflops machines. The most recent in the last few months is El Capitan, which is at Lawrence Livermore National Labs. Aurora, which is at Argonne National Laboratory, and Frontiers, which is at Oak Ridge National Lab. You may see a certain theme here. All of those machines are owned and deployed by the Department of Energy. Curiously, Aurora, which was supposed to be the first exascale machine, ultimately was announced to be the second exascale machine and achieved that. But it was also supposed to be faster than the first one, which was Frontier. That didn't happen. Aurora, through a number of missteps on the part of Intel and others, honestly required greater power, electric power, and still, in spite of the higher power and size, is still the second. Frontiers was still the first when Aurora was deployed, and El Capitan is now the first, with Aurora, I believe, still now number 3. And the rate of growth of computers continues to slow down. And this is measured by the high performance LINPACK, or highly parallel LINPACK benchmark that has been used for 30 years this year, to measure the performance. Why? The manufacturers really like it, because the bigger the program, and it does expand, the friendlier is the numbers because of the polynomial increase, factors of 2 and 3. So that makes computers look good, and newer computers look even better. HPCG solved pretty much the same problem. The conjugate gradient approach to high-performance computing, this, like high-performance LINPACK, was first developed by not good, okay, by Jack Dungara, who is just retired. Oh, and as he retired, he won the Turing Award, which is the equivalent of the Nobel Prize in computer computation. And today, the performance measured in flops is around 1%, maybe twice that, or maybe less than that. And so that is not a friendly application for the field. And to Jack's credit, he has nonetheless pushed this benchmark forward so that you have a greater sense of reality. Well, I've taken a few too many minutes to discuss the bad news, but the rest of the talk is how we plan to address all of the pieces of the bad news. A month ago, I was at the Supercomputing 24 conference in Atlanta, Georgia. And the team that represents the benchmark announces the findings of that benchmark every half year. And the benchmark, I'm showing a pie chart here, which talks about the large body of performance of, 9 different machines. 9 machines from Canada, Brazil, the Netherlands, Italy, South Korea, United Kingdom, France, and Japan. Okay, that's 9 machines, different countries. And just in case you have lost count, there are almost 200 countries in the world. In fact, all of those machines are single-digit numbers of the top 500 list. The two, which is China and the United States, are at least double-digit numbers. China currently is 12%, but that's misguiding because for reasons I still don't fully understand, China does not fully embrace the top 500 list. And then the United States, which is somewhere, and I can't even read the font, I think it's 34%. All the other countries, 20%. Now, I could have borrowed from Eric Strohmeyer, who does the documentation very effectively for the top 500 list. I could have added many pie charts. I want to give credit to Eric for this. And somehow I forgot to mention Germany. Sorry about that. But that's only one spot in the breakdown of the fastest computers in the world, at least as identified by the LINPACK or high-performance LINPACK numbers. And because that is self-selecting, that is, that people submit their findings of their benchmark runs to the governing body of the top 500 list. I tell you this so that you know that this is not an absolutely objective appraisal. There are people and machines which do not get documented by this for whatever reason. There are 3 curves on this machine. It's put together again by Eric Strohmeyer every 6 months. And what I want to show you, I should be showing you successes, and these are successes. The last 3 dots are essentially those 3 points on the red line that introduce exascale computing. The entire range of those 3 dots covers less than 1 exaflops. Frontiers is 1.1 to 1.2, and the El Capitan machine is not quite to 2 petaflops. If you look at any of these curves, in particular the bottom curve, you see that it's not a straight line. In fact, in the case of the bottom curve, which represents the 500th machine, it is clearly flattening out substantially. And that has taken place over a distance of more than 10 years. In fact, we're looking at the fastest machines. The machines that have just come online came online last month and are coming in line are greatly reduced in the growth of performance. This is a problem. In fact, this is a big problem. Did I just mess that up? No, I did it right. Okay, so looking at this table, this is the top 10 machines of the top 500 machines. If you take a moment and look at the 1, 2, 3, fourth column from the left, which turns out to be the fourth column from the right, okay, you'll see that half of them are deployed in the United States. Now, that's half out of, remember, almost 200 countries. And if you look a little bit more, you'll see that 2 of the machines, which are made by HPE, one of which is AMD, not Intel, are also made by HPE. And so it's actually 7 machines out of 10, which are, again, in the US. This is also really not good. This should be a vibrant, a constantly evolving, a rapidly evolving industry, and it's not. It's flatlined. Now, just to show you, this is, Lawrence Livermore National Labs, in which El Capitan was going through some of its final formalism. The skins are off. As you can see, tests are ongoing. And here's the postcard version of El Capitan, and it's currently now operational. It's an impressive machine. But remember, I said 10,000 square feet or 1,000 square meters. That's a big machine. The Cray 1S in 1976 was on the order of 8 square feet. I think that's right. I mean, it would have stood right here next to me. The Cray 2, some 7 years later, was only slightly larger. Not as successful as the Cray 1, but the Cray 2 was still a low platform version. That was true for the Cray XMP, the Cray YMP, let me get this right, the C90, also a derivative of the, well, ultimately of the Cray 1. And why? Because at that time, Seymour Cray had moved to start yet another company that was CCC, or, yes, the Cray Computer Company. This is the field that has, for all intents and purposes, as we understand it, come to its end. Now, let me just remind you, the earlier von Neumann architectures, over 70 years, although certainly there were changes that were made, nonetheless are derivatives of the von Neumann model. What does that mean? It means that with a shared memory architecture and then ultimately a partitioned shared memory architecture, I'll come to that in a minute, and it was essentially sequential. The core processors were incremental. They launched, I was going to say, one operation per cycle, but no, sometimes they would do 2 or 4 operations per cycle, but it was still sequential in that regard. And the main memory, which worked out of the full computer, and the sequential flow control, they were separate. The control had to reach into the main memory, do a load or store, and then execute the next instruction. And if you sat down there and counted microcycles, I should call them nanocycles, you would find that the architecture itself would spend most of its time, at least in the memory cycle, just in the communication. Oh, that, by the way, that's not a good thing. And I sort of emphasize this for a point that I will make shortly. Also, the von Neumann machines, since the early 1990s, were an extension of the conventional architectures, and they became shared memory. The shared memory pieces, we refer to them as nodes. That's misused over and over again. Those pieces were shared memory, but then the machine itself was assembled by many of those pieces. And those different pieces communicated together through a process of message passing, essentially a different form of computer. And so now you really had a machine that hierarchically had many small pieces of tightly coupled pieces, and then the whole machine as a message passing piece. And that worked very well as long as Moore's Law, which was specified in the late 1968 by Gordon Moore, who passed away within the last year or so, stated that performance overall would increase by a factor of 2 every 2 years. Now, that was just an observation on his part. He didn't actually mean it to be a prediction. But it was a prediction, and while the number 2 tended to vary, it wasn't far off, and that went on for 50, 60 years. That's a really good guess. It flatlined. I showed you the curves that were in the process of flatlining, and the reason they weren't actually flat is because they became humongous machines, large physical machines. I should also mention that El Capitan, $600 million, and it hasn't actually been fully documented yet. In fact, if you go online and you look for it, you'll find you can't find the footprint of El Capitan. They're still working that out too. All right, so enough is enough. Even though we can build them, we can't really sell them. And if we could sell them, how many people are going to be needed for that kind of money to use them? And so instead, what will happen is they'll be broken up into pieces, not physically broken up, but different parts of the machine will be allocated to different users. This is inherently a failed approach. As I'll show you in a moment, new approaches have to be taken. And I want to talk in the last few minutes about a von Neumann architecture that is currently under development, has been under development through research over the last almost 20 years, both at Louisiana State University and then at Indiana University. Let me just touch on the top points of this class of von Neumann machine. So this is a machine that is fundamentally a parallel computer from the lowest level up to the global level. It has a unified execution model, a single execution model, and as I mentioned a moment ago, the classic machines over the last, almost 30 years have been fragmented or broken up execution models. There's another opportunity, I should say, and that is executing graph computations. I'll say more about that in a moment. Efficiently and quickly. And the computation no longer being lockstep, but rather asynchronous. Now, I say asynchronous, I was looking at my slide, I said, well, it's not completely asynchronous. There is control such that the computation doesn't get out of step, but it's not at the step level, rather. It is a group of operations, all of which can correctly run out of order and still not lose the effective computation itself. I have a final major bullet there, and it says inherent graph-oriented parallel flow control for traversing graphs. And this is the key theme for the rest of the presentation. Now, in the area of non-von Neumann architecture, the class of machine that I'm talking about are memory-centric architectures. It's not a term that you use currently when you go to class, when you go to presentations and so forth, but it is receiving attention. And the research to build it up, as I think I said moments ago, was almost 20 years ago. The two other, certainly better known classes of machines are quantum computing, and you had a whole session on quantum computing here at this conference, and neuromorphic computing. And, well, as the name implies, quantum computers use quantum mechanics to do the magic of many operations in the same device at the same time. It's like magic, and giving another keynote address, I don't know, 2-3 years ago at the International Supercomputing Conference in Germany, I said that trying to explain quantum computing is like teaching quantum computing at Hogwarts. I tell you, I've been a little shy up here, and I'm glad to hear at least a trickle of laughter, because that's the best I got. I'm sorry. Quantum computing is very exciting, but it doesn't universally replace all of the forms of computing. It does certain kinds of computing that scale both polynomial and exponentially for certain kinds of workflows. And when it's doing that, in the extreme case, it will blow away anything that could be done in the lifetime of the universe. Okay, so that's a good selling thing if you're trying to sell a quantum computing program at your respective governments. Neuromorphic computing is stranger still. Neuromorphic computing either identically or at least metaphorically takes on the physical shape of, well, neurons, the brain. And there's only one problem with that. Nobody knows how the brain works. So you have people, some in the US, some in Europe, some elsewhere. I don't know if there's neuromorphic work here in South Africa. My apologies. We know the brain works. We have a proof of concept. And by the way, it's reliable, sort of. Some people live more than 100 years. They didn't used to. They're most of the lifetime of humanity. And my understanding is Homo sapiens, we are all Homo sapiens, lasted the better part of 200 200,000 years. I have a tool. I actually have a physical tool that was made before the existence of Homo sapiens. It's called a Chicxulub hammer. Right? It's really exciting. It's just a rock, but it's my favorite rock. In fact, it's my favorite part of anything. The neuromorphic computing is different. I don't have a neuron. Now, I visited in, where was it? In Geneva. I visited a research center that did both wetware and solidware. The wetware opened up brains of little animals, and the scientists I talked to were very proud of showing me this incredibly gooey and messed up brain. But also, much nicer, showed me the simulations of brainware. But they didn't know how a brain works either. They know how pieces work. And they are optimistic that they will solve the problem. And after all, it's not magic that makes this stuff work. Memory-centric architectures are, relatively speaking, new, although they have a longer history than you imagine. Graph dynamic processing is the reason that I and my team currently at the Texas Advanced Computing Center in Austin, Texas, are developing for the purpose of dramatically increasing the performance of graph problems. And not just graph problems, but graph problems that change. And not just graph problems that change, but graph problems that change their topology. And by that I mean the way they interconnect. Interconnect what? Yes, interconnect vertexes. And they connect them, not physically, but in a form that effectively implements physical change using edges. So edges, which have an input and an output, connect with vertices that may have anywhere where one or two inputs, one or two outputs, up to millions of such connections. Now, this is a form of structure that is implemented by direct flow control. And this means that parts of the computation flow through the machine. That would sound like it's more work. It's actually less work. Because when a von Neumann architecture executes one instruction at a time, well, that's the one instruction. In a graph computer, it can, as I said, it can transparently, at least in principle, send control over the edges, again, from a few edges to millions of edges. And they change the state, not just the state of the values of the machine, but they change the state of the structure of the machine as represented. This is big. Because a graph operates at near fine-grained control. Today, if you do graph processing, you're interpreting the graph at best. You're writing a program that interprets the input data structure of the graph you're trying to simulate, and then that in turn changes whatever the data structure is that you're representing. And yes, I mentioned asynchronous computing at the beginning of this presentation, and the machine that we're developing is asynchronous in the same way. The edges operate within the constraints of precedence, operate out of order. So, and this is big, this means that the communication between two vertices in the machine, if they're very close together, can communicate in one or a couple of cycles. If they're far apart, they communicate on many, maybe hundreds of cycles. But the program doesn't care. This is the big deal. This is where there's a separation between the hardware machine and the abstract execution model of the machine. Programmers don't have to worry about the order, at least to first order, and the machine takes care of at least the latencies of communication. There are special control mechanisms called futures. Future was actually invented back in the late 1970s. It was used in a number of computers. And there's a single image processing presentation of the machine to the programmer, as I mentioned a moment ago, and that means that there's a global memory management. What do we have in conventional machines? Well, you have caches. This machine doesn't have caches. You have registers. This machine doesn't have registers. You have main memory banks. Well, that would seem good, but in fact, then you fragment the main memory across the large machine. And this machine doesn't have that at all. In fact, in some ways, it goes back. It's more primitive. So here's a simple picture, as simple as I could make it. And I'm not very good at doing graphics in a PowerPoint. But so there's a vertex, and there are incoming edges, some number of them, and there are outgoing edges, some other number of all of them. That's all there is to building a graph processing machine. If you have a piece of hardware that can execute the contents of a graph in a single cycle, then you have the fastest going graph processor. I can't do that. Right. There are aspects of a physical machine that don't allow themselves to do a graph with a million edges going either in or out. But they will let you do it in polynomial space. What does that mean? That means that instead of having 1,000 edges leaving, which I can't do in one cycle, I can do it in 10 cycles. And in fact, I can do it in less than 10 cycles, and I'll explain why in a moment. So this is a memory-centric architecture. What I'm about to say is true conceptually, not quite so true in reality. And that is, there are no processors. There are no processing units. And certainly the processors don't do control. Okay, that's sort of a big deal. We did, and we do it now, conventional non-von Neumann architectures is control-centric. They have a program counter. Every one of the cores has a program counter. In fact, some cores may have more than one, not many, but more than one program counter. It's program counter driven. And I say one operation per issue, and that's not true for all machines. At most, it's a few operations per counter tick per processor core. But in the future, we're going to be memory-centric rather than processor-centric. We will have thousands of executing memory banks. I'm going to teach you a term from this called funtons. I assure you it doesn't mean anything, but it is the local, which means in a single chip, it is a local entity, all of which is wired tightly together. And there are many of them, literally thousands of them per chip. Each of those funtons has a number of, I want to say large, but now I mislead you. Okay, it's 256 bits long. I don't know if you think that's large or small, but that's the size that we're currently using. And the reason is because we want to be able to access a record in one cycle per funton. And the result of that is that all of the data from the funton can be processed in one take. Now, it's actually more complicated than that because a record within a funton can just have data. You can put a lot of data into 256 bits. It can have instructions. Well, you can put close to something like 35 bytes of control in a record. But most interestingly is you can have both. You can have an instruction and then some arguments or operands. That's everything you need to do an operation. And the memory actions are driven by the incident message packet arrivals. What am I talking about? I'm talking about edges. So edges in an abstract form arrive at a funton, specifically at a precise record, and read all the data in that record and follow through with the action. Now, we've taken it one step further. I'm not even sure if we're right about this, but I think we are. We've added tags. Tagged architectures go back decades, but mostly they go back for one or two small purposes. They may have an empty full bit. Some have played with the idea of having types in the tag. Well, we do both of that. But the main reason we adopted tags was because we needed to be able to expose all the parallelism in a record. Okay, biggest flaw of this architecture, by the way, we call it an active memory architecture. The biggest flaw of the of the active memory architecture is that we still only are executing at any one time a record. Now, it can be overlapped, probably will be overlapped, so there'll be more than one record flying at a time, but one will be completed per schedule. Here's a toy graph, just in case you were not building your image in your head while I was speaking. Those are incoming edges, and those are outgoing edges, and an actor, or more specifically a vertex, will execute when the incoming edges are available. And when available, will produce all of the output edges. And I said, The output edges are a logarithmic function, which for large numbers of edges become very small. Well, I just oversimplified. In fact, not all the outgoing edges have to go out. The vertices can be more sophisticated than I'm making them seem. Yes, they can be very simple, but they can also be complicated. They can also have conditionals that, in different ways, will fire or use only part of the incoming edges. And by the way, they don't have to use all of the outgoing edges. Again, conditionals allow the decision to be used to allow parts of the vertex to be executed. And finally, as I already said, the topology. What did I mean by topology? I meant the shape of the graph can change. And when do we use something like that? Well, how about semantic nets? Most of you don't probably know or care about a semantic net, but in fact, they have been used also for decades. And the semantic net is a topology specifically designed for the structure of, well, a dictionary, a giant dictionary, but it's constantly changing the dictionary. It's finding errors in the dictionary, finding inconsistencies between entries in the dictionary, and it's accepting new definitions in the dictionary and adding edges to it. So this is much more sophisticated. Okay, I believe I have covered all of these. Let me go through them quickly. Well, I didn't actually mention this. Graphs are defined not by temporal locality and not by spatial locality. Why is this important? Well, that's what caches use. Caches in your system use caches. And I hope I said that wrong. I bet I said that wrong. Programs or systems have caches. In fact, usually they have at least 2 and often 3. And there are some machines with 4 caches, 4 levels of caching. You can see why it may take a while to get there. Vertices are points of data. I've already explained that. Incident graph edges are the inputs that deliver results from child vertices, and the values at graph vertices can be altered with additional input edges. I've already said that. Graph topology can be altered through atomic compound operations. Wish I had the time to talk about that. Maybe next year. You'll find that for various reasons, multiple cycles are needed to protect and to change the topology. This is not a purely directed graph. That is to say, the edges do not move completely back upwards. By the way, in your brain, there are at least parts of your cerebral cortex that also send neurons up, not just down. And I did that. I said that it presents a single system image. There is one potentially humongous graph, and it sits on a humongous machine, and it's all at the same level. You can access, without any special concerns, any part of the machine from any other part of the machine. And it says all that. So we've explored over many years different designs of this. They are the pieces that I want to point out, and I already hinted at it, there aren't registers. Your machine has, your computer, your laptop, it has registers. A register is a completely different part of the namespace than the main memory. Yet you have to first deal with your registers before you can even talk to the main memory. We don't use registers. I've already mentioned the global namespace. There's a virtual version, and there's a physical version. And you can mix them. And it depends on whether something is moving or something is in a fixed physical state. The latter, you can use physical memory. The former, you have to at least introduce yourself to some of the pieces and get to the fixed parts of the code. But even the fixed parts of the code, when fixed, can move. They can move through the system. And so there's a balancing act there. Part of that can be handled by the programmer, but relatively little. More of it is handled by the runtime system, and the user uses the runtime system very little, or it can be done by a compiler and the user never sees it. Here's a block diagram only to give you a sense of what a funton looks at. In the middle, you see that there's a block, and that says data memory. Well, if I had my way, it would be data/instruction memory. But members of my team insist that having a separate instruction memory has advantages. So, well, I don't agree with them, but we're far enough away that it doesn't matter, so I let them get their way until it's time for me to tell them they're wrong. There's the handle of operons. Now, I haven't used the term operon yet. If you want to, get attention, you need to create a lot of names of things that already exist, and I'm doing that. And the operon is what anybody else would call a message, but not a communicating message. It is rather a control message. And there's a lot to talk about operons. Others you see are the context manager, and this is used for the funtons, and the execution unit also for the funtons. And then there's part of the communication, the physical communication mechanism. Now, how many different communication channels do we have leaving a funton? Well, it depends. We've selected 3. Now, that may be unimpressive, but it has the advantage of spending most of the space on funton records and least on communication. That number may change. Here is an initial instruction set architecture. I suspect that the majority of these will be used in the final instruction set. I also expect that not all of them will be used in the final instruction set. But it is an effective body of simple code that allows us to develop test programs. And it's the current that we're using. Except for, oh dear, I've lost it. Oh, no. Oh, I see. There it is. Down at the very bottom right, in blue, difficult to read, is trigger. And actually, we don't do trigger anymore. We just kept it because it was part of an earlier instruction set architecture. So it's already changing. This is the active memory architecture module. It's the current design has about 48 different sockets. The sockets have 4 different sets of funtons, and then those those chips are stacked. So you have several levels of very low level parallelism. And I know that I've left you with only a sense of what a active memory architecture looks like. But I also hope that I have left you with an understanding that it's very different. Very different. And by the way, it's easy to design. Instead of making a very complicated solution to having a very complicated design, we make a very simple design and then have them all operate together. Let me just point out a couple of numbers. This is a medium-size active memory architecture. If you look, and I'm having to look here, at the peak flops, this is 3.4 exaflops, or exaops, I should say, but it can include floating point operations. So that number is a relatively small machine. All right, it's not that small. It's about 64 racks. The count of AMA sockets is about 1 million. Okay, that's maybe 10 times as many chips as you have in most large, not the largest machines. 10 times, that's close enough, right? Other statistics, which are certainly good to 2 significant digits and pieces, have also been analyzed. If we had another 45 minutes, I would, of course, go over all of them with you. Sadly, we do not have that much time. So, with that, I close here. I thank you very much for your attention and your patience, and enjoy the rest of the conference.
Oh, one thing I failed to mention, I was an educator in my former life, so class, please indulge. Please take out your devices, everyone. Are we there? Okay, let's go to settings. No? All right. I don't know why you're laughing, but okay. When you are there, on your phone, depending on whether or not you got an upgrade, it should say vibrate or silent. Do you have that? You do. Awesome. But because our phone is with us on our hand, let us quickly go to camera. Remember, I've got an aerial view, so I can see. Are we there? All right. Then go to the selfie mode. Most of us is already there. Ladies, if you had time to change, let's wipe the camera for the foundation. Are we there? On my count, everyone, when I say 3, you're going to take a picture of self, because we're on selfie. Right. So 1, 2, 3. Then something that I want to teach you, because most of you here it's your first time at Tabeja. We call it GQ in the event that you can't pronounce. I know there's a Poppy Act, so just quickly wink to your neighbor as permission. I need you to tilt your phone so you can see either the deco or the person next to you, the hashtag I was here, all right? Or towards me as your MC, are we there? Okay, have you tilted it? On my count, you are going to take a picture. So this is a condensed, ne? I know you're busy with formulas and I was downstairs and I left there with palpitations, so here. Okay? 1, 2, 3. And the very last one, I promise, please go to video, still on selfie mode. We're there. Now press record for this to work. So press record, the red button. So it should be moving. You should be on about 3 or 4 seconds. Are we there? Now I need you to tilt your phone to a different angle. Everyone. And then on my count for this one, I need you, when I say 3, and you have to do this, you need to laugh. Okay. So 1, 2, 3, laugh. Thank you so much. All right. The video is only meant to be 3 seconds. Thank you. Now, ladies and gentlemen, the reason why I always start with this icebreakers and MCs, number 1, I say take a picture of self because more often than not, you always concentrate on other people, other organizations, and so forth, so don't forget self. 2, I said please tilt your phone so that to show you in everything in life, in the context of everything, don't forget yourself in the midst of everything. Then the last one, the third one, and the reason why we're here, and that is a prize giving, is that through it all, find a moment to laugh because pain locates itself. So whatever the outcome tonight, whether or not you come on stage to receive a reward, for me, the prize giving is what I saw downstairs. And that was the hubs and the stations and the clusters, the networking. For me, that was the actual prize. But as we know in life, there must be a winner. So welcome, and thank you once again for joining us. And so tonight is us celebrating, acknowledging the hard work and the performance of students who participated in the poster session, the Datathon Challenge, and the Sanren Cybersecurity Challenge, and the CHPC Student Cluster Competition. I'd like to introduce our DJ for the night, Danny. If you can wave, he's there. There he is. A round of applause, please. Danny is for phase 3. We are now in phase 2. Ne? So without any further ado, I'm going to hand over to Dr. Happy Sitole, the Center Manager of NICIS, to do the official welcome.